All right, Laia. So thanks for joining me. I'm really excited to talk about the feedback we got from our latest roundtable. I think it was such an interesting discussion. We had such a great representation across the healthcare and pharmaceutical space. And so, for the group and for everyone watching, we're going to kind of break down some of the interesting applications and use cases that came out of that. So I guess just diving into it, just to start, one of the first applications that came up was machine learning in clinical trials to validate and ensure the patient data quality. And that was an interesting one because I think on the face of it, that's not necessarily a quantum problem, but there is this concept of detecting outliers that might be an interesting quantum use case. So would you mind talking through that a little bit?
Sure. So regarding data quality, there are two things. One would be the data format. Like this variable should be within this range, or it should be a string rather than a number, these sort of things. So I think these kind of problems are not really quantum. It's just passing the data through some classical filters. So if this is really the bottleneck of the problem, I don't think it should allow for quantum solutions. But there's another angle that we can look this problem with, which is outlier detection. So if you want to detect that the data might not be right because it's weird, it's not in the normal distribution. It's so here we could use quantum algorithms to detect outliers, and I think this is very relevant because quantum circuits could help us translate and move the data from a classical space to a quantum space, which might be a higher dimensional space, which provide more useful information than the classical ones. So this is very related to kernel methods, and for example, with supervector machines, where you're doing exactly this. So this could be used to perform outlier detection and detect those data samples that might not be correct because they are fairly different from the rest. So this is one of the approaches.
Yeah, that's really interesting. And aside from just high impact of having, really solid patient data and data quality, it's also a huge regulatory issue as well, just making sure that everything's buttoned up.
Yeah, it's something that has to be done, so it's really relevant for that.
Yeah, so an interesting one to dig into. So the second one that came up, and I feel like they get increasingly more interesting as we go through this, was drawing the correlations between blood samples and mapping them to what is a really vast kind of disease space. Can you talk a little bit about the kind of machine learning approaches as well as how we can leverage optimization for that?
Yeah, so with this problem, the thing was that the data sets were very, very small. So you could not use very large machine learning models like neural networks. So rather, the question was selecting the optimal machine learning models, which are simple but describe the data properly. So they were using models like logistic regressions, which are super simple. But the problem is that there are a lot of simple methods that could be used. So exploring all the types of machine learning models or the loss functions, the optimizers, the hyperparameters of the models, this was a really challenging task because we had to look for the optimal, very specific model within a wide range of possibilities. So here is where quantum could help. And I see two approaches. One would be using quantum annealing to solve an optimization problem. So if we could somehow write this task as an optimization problem, then we could use the quantum annealers from D-Wave, for instance, to look for the optimal solutions. But this is something that we have to discuss further because I don't know how easy it is to formulate this problem as an optimization problem. But then there's another approach that would be to use quantum Bayesian optimization. So I would say that there are basically two ways to explore the hyperparameter space. One would be just doing grid search, which is basically brute force. Just try all the possibilities and select the best ones. And there's another one which is called Bayesian optimization, where you're not just looking randomly, but you're looking in the direction which is more likely to give optimal performance. And this is a classical algorithm and it works well, but it takes a lot of time to explore all the optimization space. So developing a quantum version of that, I think it's shorter term and it's more feasible. And I think it might provide advantage for this problem.
Oh, that was going to be my next question is how long term are we looking at with this and really the other one on validating the patient data quality? Both of those feel relatively near term and something that we can at least start exploring as far as our library, you think?
Yes. So this one about selecting the optimal hyperparameters, I think both quantum annealing and Bayesian methods are short term. So I think if we can get more information on and really quantify what kind of machine learning models are using, where is the bottleneck of the problem, we could see which of the two approaches makes more sense. But both of them are shorter term. And the other one regarding the data quality, it's also shorter term if it's a problem of detecting outliers. If it's a problem of data format, of course, that's just a classical problem. And yeah. But yeah, I think both of them are quite short term.
Okay, so that's exciting when we start bubbling up some of these ones that we might be able to kind of expand in our library and start getting people using sooner rather than later. So yeah, that's really exciting. Another interesting point that came up, this wasn't a use case, but someone brought up an interesting point around the fact that these algos are going to need to evolve with larger and more diverse data sets. And we talked a little bit about like the CNN algo that we've developed, right? We used a very specific data set that's solving a very specific problem. Can you talk a little bit about how, I guess, we think about, applying these algos to specific use cases and how we see that scaling?
Yeah. Well, first of all, I have to say that we always try to apply our algorithms to problems that are meaningful. So we're already providing a useful quantum use case. So this algorithm is already being applied to something useful, which is something that not everyone does. In research papers, it's common to use popular benchmarks to assess your algorithms, even though they might not represent real data. So this is one thing. But apart from that, of course, we want the algorithms to be as general as possible, and we want to reach as many use cases as possible. So basically, when we have an algorithm, we're going to try to generalize it so that it can be applied to other problems, and then develop the library, and of course, use the help from people who actually try this algorithm on other use case and learn from them. If users use our library and they think there's something missing, we're going to develop it and add it to the library. So it's really helping learning from the users.
And coming use case first, right? So making sure that it's not just a random suite of algorithms without a clear path of how they can be applied, but that we're actually trying to pluck out the problems and create the variations based on the problems that come up. And that's why I'm really excited to build a community and really build, the users around this to kind of help shape what it needs to look like and what variations we do need to see across those. So there will be lots of interesting, I think, conversations to come as we continue to get, build up those users and subscribers and start testing these across different use cases. So now looking at more of the specific algos that came up that don't fully tie to the end use cases, physics-informed neural networks was one that came up. How do you think about this and what opportunities and potential applications do you see there?
I think it's a very relevant algorithm and that we definitely should explore it more. So physics-informed neural networks are those which use the physical knowledge from the problem to help train the neural network. So for instance, if in your problem there's an energy conservation requirement, you can add that to the neural network so that it has this information and it doesn't have to learn it from scratch. So these are the kind of problems that physics-informed neural networks use. And I think it's very relevant because quantum computing is also a physical system. So there might be a way to tie these two concepts. And it's not really the same thing, but there's another algorithm which is called quantum reservoir computing, which uses a quantum system, the evolution of a quantum system, to extract useful features from data and to perform classification and regression and forecasting tasks. And this is a bit the same idea because you're using the knowledge of the quantum system to actually make predictions. So I think physics-informed neural network are slightly different, but I think they're worth exploring and see how we can match the two algorithms together.
It seems like a natural, elegant math overlay,
Yeah,
right?
exactly. It seems like there should be room for improvement there.
Yeah. Okay. So that's an interesting one for us to continue to dig into. And then the other one, this keeps coming up actually, tensor networks. And while those aren't quantum algorithms, they're quantum inspired algorithms. Can you talk a little bit about, I guess, the nature of those algorithms, how they're a little bit different, and what some of the near term applications are with them?
Yeah, tensor networks definitely have a huge potential. So tensor networks work with tensors, which are basically high-dimensional matrices. So a 3D matrix or a 4D matrix or NZ matrix at the end. These are tensors. And there are a lot of things that can be done with tensor networks. But basically what tensor networks do is they do operations with these tensors to simplify them and approximate them in a very clever way. And they use the principles of quantum mechanics to do that. And I think there are a lot of applications of tensor networks, and they're going to keep surprising us through time. But one of them that I think is very relevant for us is neural networks compression, which means that when we use neural networks, they're highly complex models. So they have a lot of training parameters. So when you're training them, you have to use very large data sets. There are long training times, and there might be problems in the conversions of these methods. So really finding simpler models that provide the same output, it's very relevant. So tensor networks can help us here to produce simpler neural networks that still predict the same output, but in a much more efficient way. So this is one application. There's also an application regarding filling the missing values of large tensors, which is a highly challenging thing. So yeah, by approximating these tensors, tensor networks can help filling out the missing values of large tensors. And I'm sure there are
So many.
more, but yeah.
I'm sure it'll keep coming up, but that's
Yes,
definitely
yes.
one to keep exploring. And I think we've got some really great short term applications, especially around the neural networks space, and more specifically the CNN. When we were kind of shopping that out and speaking to people, some of the more specific applications that came out of that we still need to dig into were above and beyond the protein binding that we're working on with Purdue, Parkinson's diagnostics, because I was told that it was really great at detecting subtle movements. And so that was a big, area to explore. And because of the detection of the subtle movements, another area was detecting those subtle changes in animal clinical trials. So anywhere that we're kind of looking at video diagnostics or something where we really need to detect the subtlety there, that was one that came up. And then we've also talked about the just generic medical imaging kind of detection that we've seen across there. So I think there's the neural network space generally, I think there's a lot of opportunity there. And just for everyone's awareness, we are going to be doing a follow-on event where we dig deeper into those. But one of the longer term applications, and interestingly, that came out, just so that people are also aware of those, was actually applying NLP and quantum NLP to the insurance space. Do you want to talk a little bit about that one and why we also view that being longer term?
Yeah, NLP stands for natural language processing. Yeah, and it means dealing with text that provide data from patients in insurance tasks. So yeah, it was mentioned that it was very relevant for them to have more efficient ways to tackle with this, to work with this text data. And I think quantum computing can have a very big impact in NLP, but it's really a longer term impact because it would require having many more qubits than the ones we have today, and having error corrected qubits so that they are resistant to noise. And so this is a bit longer term. And I know there are models being developed today in quantum NLP, but they're still dealing with more like simpler grammatically speaking language models, but there's a lot of room for improvement here, and it really does have a lot of potential, but we will have to wait some years for that.
Yeah. Well, it's good to start categorizing these, right? And starting to understand what buckets they sit in so that we know we're at least focusing on ones that we can get people using sooner rather than later. But it will be an exciting one to dive into once we're ready to get into that space. Anything else, I guess, Laia, that you want to cover with the people watching?
Well, we will have another session on neural networks. But yeah, we're doing some interesting work with Purdue, with the Purdue team. So we're also tackling this, predicting the binding affinity for a potential drug and the target proteins. And so we already developed a 3D CNN method to reduce the training times of the classical 3D CNNs. But with them, we're developing a fusion model. This means that we're taking two very powerful classical machine learning models and we're combining the information that they extract to make even better predictions. And we're using quantum neural networks to make these predictions. And they're giving very interesting results. So we will talk a bit more about that. Yeah, it's exciting. It's very exciting.
Yeah, that's going to be a good one. All right. So those that are watching, our next event on the neural networks, the quantum neural networks and their applications, is on April 3rd. And we will be also holding a series of these where we dive into just the broader use cases and applications so that we can continue to hear from everyone. So if you want to chat, if you want to discuss a project, don't hesitate to reach out. But otherwise, stay tuned for the future events and recordings. Thank you.